Module 7, Lecture B, Sequence Models. By the end of this lecture, you will be able to build LSTM or GRU-based sequence models for text classification using tf.keras, implement a simple transformer-style encoder block using Keras layers for sequence modeling, and evaluate and compare the performance of different sequence architectures on an NLP task. Recurrent neural networks, LSTM and GRU essentials. In language sequence models, LSTMs and GRUs are important because they can preserve useful information over many time steps. Unlike simple recurrent networks, where the influence of early words quickly fades, these models use gates to control what information is kept, updated, or forgotten. This gating mechanism helps maintain context across a sequence, which makes LSTMs and GRUs well-suited for tasks such as sentiment analysis, topic labeling, and intent detection in dialogue systems. An LSTM cell manages two kinds of information: a long-term memory that flows through the sequence, and a short-term activation that is updated at each step. Inside the cell, gates decide how much past information to keep, how much new information to add, and what to output. This design works well when a model must remember something for a long time and use it later, such as in text where the key opinion appears after a long context. Gated recurrent units simplify this structure by combining some gates and using a single hidden state, yet they are still effective for tasks like text classification and often match LSTM performance while being simpler and faster. Choosing between LSTMs and GRUs is mainly about trading off model expressiveness, speed, and what your dataset requires. LSTMs are better for very long sequences and capturing subtle long-range relationships, while GRUs are simpler and faster, making them suitable for shorter texts and quicker experimentation. In both cases, the models process token sequences through stacked recurrent layers, often with dropout and dense layers for classification. Their key strength is maintaining and updating context over time, so they can turn sequences into useful features for accurate predictions. Python code, LSTM and GRU essentials. This material introduces simple examples of using LSTM and GRU layers to build small text classification models with TensorFlow. It focuses on the core ideas behind recurrent sequence models rather than detailed implementation steps. By studying these examples, you learn how recurrent networks process sequences and apply them to basic text classification tasks. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version, make sure the script runs with the intended library setup. This is important for compatibility because different versions can change how features or functions behave. It also supports reproducibility, so others can run the same code and get consistent results. We start by importing three key Python libraries. The operating system library lets us interact with the system, for example, to work with files or environment variables. The random module provides tools for generating random numbers and shuffling data. Finally, we import the numerical computing library, often shortened to a brief name, which we will use to handle arrays and perform efficient mathematical operations. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes it easier to create neural networks. From Keras, we import the layers module, which provides key components such as dense, convolutional, and recurrent layers, including LSTM and GRU. Together, these imports give us the essential tools to construct and train recurrent neural network models for text classification. To get consistent results in our experiments, we fix the random seed to a specific value, such as 42. We first set this seed for Python's built-in random number generator, then for NumPy's random number generator, and finally for TensorFlow's random number generator. This makes all random operations, including things like initializing neural network weights, behave the same way every time we run the code. Such a deterministic setup is essential for reliable debugging and for fairly comparing model performance across different runs. This code displays the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility with your project. It also lets you confirm that the intended version is installed. This is especially useful when working with specific features or debugging problems caused by version differences. We begin with a small text dataset made of 6 short sentences, each expressing a different opinion about movies from positive to negative. This dataset will be used to train and evaluate text classification models. Each sentence is stored as a string in a list, which makes it easy to handle and process the text later in the script. We use a NumPy array to store binary sentiment labels for each text sample, where 1 means the sentiment is positive and 0 means it is negative. This array directly maps each piece of text to its sentiment. We set the data type to 32-bit integers so it works smoothly with TensorFlow operations used later in the workflow. We use Keras's text vectorization layer to turn raw text into sequences of integers that a neural network can process. We limit the vocabulary to the 1,000 most frequent words so the model focuses on the most important terms. Each text input is then represented as a sequence of 10 tokens, with shorter text padded and longer ones truncated to this fixed length. By configuring the layer to output integer sequences of this length, we prepare the text data in a consistent numerical format suitable for training neural network models. The vectorizer is first adapted to the small text corpus so it can learn the vocabulary and how often words appear. Pause. This preparation step allows the text vectorization layer to convert raw text into numerical sequences. Pause. These sequences are essential for training machine learning models. By fitting the vectorizer to the specific dataset, it can efficiently tokenize and encode the text into a format suitable for neural network input. We first turn the list of text strings into a TensorFlow constant so the text can be handled as a tensor for later operations. Then we pass this tensor through the text vectorization layer. The vectorizer converts each text string into a sequence of integers, where each integer stands for a token from the original text. This numerical representation is essential because neural network models work with numbers, not raw text. The code prints the shape of the vectorized sequences tensor to verify the dimensions of the data after converting text into numerical form. This check confirms that the text vectorization step produced data with the expected size. Ensuring the correct output shape at this stage is important because later steps in building and training the model depend on these dimensions being accurate. We split our dataset into training and validation sets to see how well the model can generalize. The first 4 sequences and their corresponding sentiment labels are used for training, so the model learns from these examples. The remaining 2 sequences and their labels are reserved for validation, meaning they are only used to test the model on data it has not seen before. This separation helps us fairly evaluate the model's performance beyond the training data. We define a function that builds and compiles an LSTM model for binary classification. It takes the vocabulary size and sequence length, creates an input layer, and passes it through an embedding layer that maps words to dense vectors of size 16. This is followed by an LSTM layer with 16 units to capture temporal patterns in the sequence. The output then goes to a single neuron with a sigmoid activation, which produces a probability for the two classes. The model is compiled with the atom optimizer, binary cross-entropy loss, and accuracy as the evaluation metric. We define a function that builds a GRU-based neural network for binary classification. It takes the vocabulary size and sequence length, creates an input layer, and passes it through an embedding layer that maps tokens to dense vectors of size 16. This is followed by a GRU layer with 16 units that processes the sequence. The final output layer is a single neuron with a sigmoid activation, and the model is compiled with the atom optimizer, binary cross-entropy loss, and accuracy as the evaluation metric. The function then returns this compiled model ready for training. We build two separate sequence models, one based on LSTM layers and the other on GRU layers. Each model is created by calling its respective construction function and providing the maximum number of tokens and the maximum sequence length. These parameters define the vocabulary size and the length of input sequences the models can handle. With this setup complete, both models are ready to be trained on text data, allowing us to compare how LSTM and GRU architectures process sequences. We train the LSTM model using a fit function that takes training sequences and their labels as input. The model runs for 10 epochs, meaning it goes through the entire training set 10 times and uses a batch size of 2, updating its weights after every 2 samples. We also supply separate validation sequences and labels, so we can track how well the model performs on unseen data during training. The training output is silenced by setting the verbosity to 0, which keeps the console free of progress messages. We train the GRU model using a fitting procedure that takes training sequences and their labels as input. The model runs for 10 epochs, meaning it passes over the entire training set 10 times and uses a batch size of 2, so it updates its weights after every 2 samples. We also supply separate validation sequences and labels to track how well the model performs on unseen data during training. The training is run in silent mode with no progress messages, allowing us to quickly train the GRU model and evaluate its performance. To assess how well the LSTM model performs, we run it on the validation dataset using the model's evaluation function. We provide the validation input sequences and their labels, and the function calculates the loss and accuracy on this data. Detailed output is turned off, so we only obtain the final results. The function returns 2 values, the validation loss and validation accuracy, which we then store for later analysis. Next, we evaluate the GRU model using the validation data to measure how well it has learned. The evaluation step computes the loss and accuracy on the validation sequences and their labels. These 2 results are saved separately, one representing the validation loss and the other the validation accuracy. The evaluation is run in silent mode, so it does not print any progress or output to the console. The code prints a brief comparison of how well the LSTM and GRU models perform on the validation data. It reports the validation accuracy for the LSTM model, rounding the value to 3 decimal places, and then does the same for the GRU model. This rounded output makes it easy to quickly see and compare the performance of the 2 models. We now introduce 2 new text samples to test sentiment prediction on unseen data. The first sentence expresses a clearly positive opinion. "I really enjoyed this wonderful movie." The second sentence expresses a clearly negative opinion. "This was a horrible and dull film." Together, these examples help evaluate whether the model can correctly identify positive and negative sentiment in new movie review sentences. To use new sentences with our models, we first convert the text into numerical form with the vectorizer. We create a constant tensor from the new text and pass it to the vectorizer, which turns each sentence into a sequence of integers. These integers represent words according to the vocabulary the vectorizer learned during training. This process prepares the new text so the models can accept it as input and generate predictions. We generate sentiment predictions by feeding the new vectorized text sequences into the LSTM model to obtain predicted probability scores. We then pass the same process sequences through the GRU model to get its corresponding sentiment probabilities. Both models run with no intermediate output displayed, since the verbosity setting is turned off. The code loops through each new sentence and its index, printing the sentence first. It then prints the predicted sentiment probabilities from both the LSTM model and the GRU model. These probabilities are rounded to 3 decimal places to make them easier to read. This setup makes it simple to compare how each model evaluates the sentiment of the new sentences. This script shows how to use LSTM and GRU models in TensorFlow for simple text sentiment classification. It prepares a small set of movie reviews with positive or negative labels, converts the text into integer sequences, and splits the data into training and validation sets. 2 models are built, one with an LSTM layer and one with a GRU layer, each using an embedding layer and a final dense layer with a sigmoid activation for binary output. Both models are trained and evaluated on the validation data, and their validation accuracies are printed for comparison. Finally, the script uses the trained models to predict the probability of positive sentiment for new sentences, illustrating how these recurrent networks capture sequential patterns in text for classification tasks. Bidirectional RNN layers. Bidirectional recurrent layers improve recurrent neural networks by processing a sequence in both forward and backward directions at the same time. This means the model can use not only past information, but also future context, which is especially important in language tasks where the meaning of a word or the sentiment of a sentence often depends on what comes next. By running one network forward and another backward, and then combining their outputs, each position in the sequence gets a richer representation that reflects both earlier and later elements. In text classification, using a bidirectional LSTM or GAR lets the model consider the entire sentence before making decisions. One network reads the sentence from start to end, and another reads it from end to start, and their hidden states are combined into a richer feature representation. This structure captures complex patterns and long-range dependencies that a single-direction model might miss. As a result, in tasks like analyzing customer emails or detecting toxic comments, the model can better pick up subtle cues and resolve ambiguities. In text classification models, bidirectional recurrent layers are often placed right after the embedding layer to add context to each token. These layers output context-rich vectors that must then be condensed into a single fixed-size representation for classification. This condensation can be done with pooling, by taking the final states, or by using attention to emphasize important positions. The choice of method changes how information is summarized and can affect performance, with simple pooling often sufficient for short texts and attention more suitable for longer, complex documents. Python code. Bidirectional RNN layers. This script demonstrates how to use bidirectional recurrent neural network layers in a simple text classification task. It builds a very small example model that processes text data and assigns class labels. The focus is on showing the structure and behavior of bidirectional layers rather than on a complex application. The example is designed to run quickly and produce clear, concise output, so you can easily see how the model performs. The commented line is suggesting that you install TensorFlow version 2.20.0. This command would normally be run in a terminal or notebook to make sure that specific version is available. Doing this helps ensure the script is compatible with TensorFlow, since different versions can change features or syntax. In short, it is there to lock in the correct TensorFlow version for the code to run properly. We begin by importing 3 key libraries that support data work in our script. The operating system library lets us interact with the system, such as working with files or environment settings. The random library provides tools to generate random values and perform random operations, adding variability where needed. The numerical computing library, NumPy, allows efficient handling of arrays and fast mathematical calculations. Together, these imports provide the basic tools for data manipulation and processing in the program. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers tools from Keras, which provide components like dense, convolutional, and recurrent layers. Together, these imports give us the basic tools needed to define and train our neural network model. We begin by setting a fixed seed value of 42 so that random number generation is reproducible each time the program runs. This means the same sequence of random values will be produced on every execution. We apply this seed both to Python's built-in random number generator and to NumPy's random number generator. As a result, any random operations that use either system will behave consistently across runs. We set the random seed for TensorFlow using a predefined value so that any random operations it performs will always give the same results each time the code runs. This makes the behavior of the model predictable and consistent. Such reproducibility is important for running experiments, comparing results, and debugging issues reliably. This line checks and prints the version of TensorFlow currently in use. Knowing the exact version helps confirm that your environment is set up correctly and is compatible with your code and its dependencies. It is especially useful when debugging or sharing your work, because different TensorFlow versions can have different features or behaviors. We create a small text dataset made of 6 short movie review sentences, each with a clear positive or negative sentiment. Some sentences express positive opinions, such as loving the movie, praising fantastic acting and story, or calling the film great and inspiring. Others express negative opinions, such as describing the movie as terrible and boring, hating the plot and characters, or calling it bad and disappointing. This simple labeled dataset will be used to train a text classification model to recognize sentiment in movie reviews. We represent the sentiment labels for our text dataset as a numeric array, where each label matches one piece of text and indicates whether its sentiment is positive or negative. In this setup, the value 1 stands for positive sentiment and the value 0 stands for negative sentiment. The labels are stored as 32-bit integers to keep the data type consistent and to ensure they work smoothly with TensorFlow operations used later in the workflow. We begin by adding a text vectorization layer as a pre-processing step for our text data. This layer limits the vocabulary to the 1,000 most frequent words and converts each input into a sequence of 10 integers. Each integer represents a tokenized word, so the text is transformed into a fixed-length numerical sequence. This numerical format is what the neural network can read and learn from during training. The vectorizer is first adapted to the small text corpus, so it can learn the vocabulary and structure of the sentences. During this step, It builds a mapping from words to integer indices based on how often and in what order they appear in the data. This configuration is essential because it prepares the vectorizer to turn raw text into numerical representations. Those numerical representations can then be processed effectively by the neural network. We first convert the list of text strings into a TensorFlow constant, so the data is in a form that TensorFlow can work with. Then we pass this constant through the text vectorization layer. This layer turns each text string into a sequence of integers, where each integer corresponds to a token from the original text. By doing this, we transform the raw text into numerical data that a neural network can understand and process. Before building the neural network, the code checks the shape of the vectorized text data. This confirms that the text has been correctly converted into numerical form and that its dimensions match what the model expects as input. Verifying the shape at this stage helps catch mismatches early and prevents errors during training. In short, it is a quick validation step to ensure the data is properly prepared for the model. We begin by choosing an embedding dimension of 16, which sets the size of the vector space used to represent words and capture their semantic relationships. Then, we define the input layer in Keras so that its shape matches the sequence length of the text data. This input layer is the model's entry point, where each text sequence is fed into the network for further processing. We begin by adding an embedding layer to the model, which converts each input word from an integer index into a dense vector of fixed length. The total number of possible words is controlled by the maximum number of tokens, and the length of each vector is set by the embedding dimension. This process lets the model represent words as points in a continuous vector space, making it possible to learn and capture meaningful semantic relationships between words and the text data. We add a bidirectional LSTM layer to the model, so it can read the input sequence both forward and backward, capturing context from both directions. This layer has 16 units and is configured to output only the final hidden state, instead of the full sequence of states. By using this setup, the model can better capture dependencies in the text and form a richer overall representation of the input. We now add a dense or fully connected layer to the model with 16 units, so it produces an output vector of length 16. This layer uses the rectified linear unit, or ReLU, as its activation function to introduce nonlinearity. That nonlinearity lets the model learn more complex patterns in the data. Overall, this layer helps the model better extract and transform features from the previous layer, preparing them for the final classification step. We complete the model by adding a final dense layer with a single neuron that uses a sigmoid activation function. This function outputs a value between 0 and 1, which can be interpreted as a probability. That probability represents how confident the model is that the input belongs to the positive class. In this sentiment analysis task, that output is used as the predicted sentiment, indicating whether the input text is positive or negative. In this step, we create the Keras model by connecting the defined input layer to the final dense layer that produces the classification output. The input layer specifies the expected sequence length, and the dense layer determines the prediction for each input. By linking these layers into a single model object, we complete the neural network architecture. This finished model can then be compiled and trained on data. The model is now being compiled for training using the Atom Optimizer, which is well suited for handling large datasets and many parameters. The loss function is binary cross-entropy, appropriate for tasks where the goal is to distinguish between two classes. During training and evaluation, the model also tracks accuracy, so we can see how often it correctly predicts the sentiment labels. The model is trained using a fit procedure that takes the vectorized text data and their labels as input. Training runs for 10 epochs, so the model goes through the entire dataset 10 times. A batch size of 2 is used, meaning the model updates its weights after every 2 samples. The training is set to run silently, with no progress messages shown during this process. The code evaluates the trained model using the same small dataset it was trained on. It calls the model's evaluation function with the vectorized text data and their labels to compute performance. During this process, it runs silently without printing any messages. The resulting loss and accuracy values are stored as the model's performance metrics on this data. The code prints a brief summary of how well the bidirectional model performs by showing its accuracy. It uses a print statement that displays the phrase bidirectional model accuracy, followed by the accuracy value. This value is rounded to 3 decimal places, so it is easier to read and interpret. Overall, this output gives a quick overview of the model's performance on the dataset. We begin by creating a constant tensor in TensorFlow that holds a single sentence. The movie was surprisingly good overall. This step prepares the new text we want to evaluate with our trained model. By turning the sentence into a TensorFlow constant, we put it in the proper format for later processing. This allows the model to carry out tasks like vectorizing the text and making a prediction. The code takes a new sentence and uses the text vectorization layer to turn it into numbers, because the model can only work with numerical input, not raw text. This vectorizer was previously fitted to the training data, so it knows how to map each word to an integer. By converting the new text into a sequence of integers that represent its words, the data is put into the right format. This prepares the sentence so the trained model can process it and make a prediction. The code uses the model's prediction function on the vectorized new text to obtain a probability score. This function runs the input through the trained model and returns the prediction as a 2-dimensional array. The verbose setting is turned off, so no extra information is printed during this step. Finally, the code takes the first value from the result, which represents the probability that the new text has a positive sentiment. This code prints the predicted probability that a new piece of text has a positive sentiment. It takes the model's output, which is a probability value, and rounds it to 3 decimal places to make it easier to read. The rounded value is then included in a short message that states how likely it is that the sentiment of the text is positive. This script builds a simple sentiment analysis model using a bidirectional LSTM network. It starts with a small set of movie reviews labeled as positive or negative, then uses a text vectorization step to turn each sentence into a sequence of integers. The model includes an embedding layer, a bidirectional LSTM, a dense layer, and a final sigmoid output for binary classification, and is trained with binary cross-entropy loss and the atom optimizer. Because the dataset is tiny and simple, the model quickly reaches high accuracy on this data. Finally, the script tests the model on a new review and outputs the probability that its sentiment is positive, illustrating basic generalization to unseen text, though in a limited way due to the small scale of the example. Handling variable sequences. When using recurrent models like LSTMs and GRUs for text, a major issue is that real sequences have different lengths. To train efficiently, we group sequences into batches, but they must all share the same length, so we pad shorter ones with a special placeholder. This padding lets the model tell real data apart from padding, which is important for both speed and accuracy in language tasks. Effectively handling these variable-length sequences is essential for realistic language processing. When working with variable-length sequences in recurrent models, We must represent the text numerically and clearly mark which parts of each sequence are meaningful. We convert text into token indices and then pad or cut sequences to a fixed length to balance coverage of long examples with memory limits. During modeling, we use a mask that flags valid time steps, so LSTMs or GRUs can ignore padded positions and focus only on real data. This is especially important in tasks like sentiment analysis, where predictions should depend on actual content rather than padding. Proper masking leads to outputs that better reflect the true sequence while improving both efficiency and accuracy. When working with variable length sequences in recurrent models, you must decide whether to use only the final hidden state or the full sequence of states. For tasks like text classification, using the final state works well, but only if masking ensures it corresponds to the last real token rather than padding. This masking lets both short and long texts produce accurate summary representations. It is also important to batch sequences of similar lengths to reduce padding, which improves training efficiency and stability. In domains with very uneven sequence lengths, such as legal or clinical texts, careful choices about sequence length, padding, and batching are especially important for effective training. Python code, handling variable sequences. This material introduces a small LSTM-based text classifier that demonstrates how to use padding and masking. It focuses on how to handle input sequences of different lengths so they can be processed together in a single model. The main goal is to show the practical use of these techniques in a simple, clear example. The line starting with an exclamation mark is a shell command that installs TensorFlow version 2.20.0 rather than being Python code. It is used to make sure that this exact version of TensorFlow is available before the script runs. This matters because different TensorFlow versions can change features and behavior. By specifying the version, you help keep the code consistent and compatible with the rest of the project. This script begins by importing 3 key Python libraries to prepare for data processing tasks. It imports the operating system library to work with files and directories, the random library to generate random numbers and make random choices, and the numerical computing library NumPy to handle arrays and perform efficient mathematical operations. Together, these imports set up a basic environment for managing data and performing numerical computations within the program. We start by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. From Keras, we then import the Layers module, which gives us essential building blocks such as dense, convolutional, and recurrent layers. These components allow us to define and assemble the architecture of our neural network model. We set a seed value so that any random operations in our code give the same results every time we run it, which is essential for reproducible experiments and model training. First, we fix the seed for Python's built-in random number generator. Then we do the same for NumPy's random generator. Finally, we set the seed for TensorFlow's random generator so that operations like initializing neural network weights are consistent across runs. Together, these steps ensure that all sources of randomness in our program behave predictably. This line of code displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because it can affect compatibility with other tools and help with debugging issues. We begin by creating a small text dataset made of short phrases that express either negative or positive sentiment. These phrases range from simple words like bad and good to slightly longer expressions such as very bad or really good movie. This collection of texts will later be used to train a model to classify sentiment. It also serves to show how to work with input sequences that have different lengths. We create an array of sentiment labels using a numerical library where each label matches one text in the dataset. A label of 0 represents negative sentiment, and a label of 1 represents positive sentiment. We set the labels to use 32-bit integers so they work smoothly with TensorFlow operations later in the workflow. We use a Keras text vectorization layer to convert text into numerical form for a model. It is set up to recognize up to 100 distinct tokens, such as different words or symbols. The layer outputs sequences of integers, where each integer represents a token. Every sequence is fixed at length 5, so all text inputs are padded or cut to this size, keeping them uniform for later processing. The vectorizer is first adapted to the small text dataset so it can learn which words appear and how often. By analyzing the text in this way, it builds a vocabulary and understands word frequencies. This preparation step is essential because it enables the vectorizer to turn the original text into numerical sequences. Those numerical sequences are then ready for further processing by the model. We start by turning the list of text strings into a TensorFlow dataset so we can process each piece of text efficiently. We then apply a vectorizer function to every text element in the dataset, which converts each text into a sequence of integers representing tokens. After this transformation, we convert the dataset of integer sequences into a single NumPy array. This array stacks all sequences together in a format that can be directly used as input to a machine learning model. We loop through each original text and its padded sequence, printing the text, an arrow, and then the sequence of integers. This lets us see exactly how each piece of text was converted into numbers. By comparing the original text with its padded version, we can quickly check that padding and vectorization were applied correctly. This simple visual check helps confirm that the text preprocessing step is working as intended. The code prints the shape of the sequences array to confirm that the padded data has the correct dimensions. This check ensures that every sequence has been padded to the chosen maximum length. Verifying the shape in this way helps guarantee that the input data is consistently formatted before it is passed into the neural network. We build a simple Keras model for binary classification by first choosing an embedding dimension of 8, which sets the size of the dense vectors representing each token. Pause. The model begins with an embedding layer that maps input tokens into these vectors, uses the maximum number of tokens as the input size, applies masking to ignore padding, and fixes the input length to the maximum sequence length. Pause. After this, an LSTM layer with 16 units processes the embedded sequences to capture temporal patterns. Pause. Finally, a dense layer with 1 unit and a sigmoid activation produces a probability score for the binary decision. The model is now being compiled, which prepares it for training. It uses the Atom optimizer, a common and efficient choice for training large and complex models. The loss function is binary cross-entropy, which is appropriate when the task is to distinguish between two possible outcomes. The model's performance will be measured using accuracy, indicating how often its predictions are correct. The model is trained using a fit function that takes the input sequences and their labels. It uses a batch size of 2, so it updates its parameters after processing 2 samples at a time. Training runs for 10 epochs, meaning the model goes through the entire dataset 10 times. The verbose setting is turned off to suppress training progress messages and keep the console output clean. The code checks how well the model performs on the same small dataset it was trained on by calling the model's evaluation function with the input sequences and their labels. This function calculates the model's loss and accuracy on that data. Progress messages are turned off, so nothing is printed during evaluation. The resulting loss and accuracy values are then stored for later use or inspection. The code reports how well the model performed by printing its main evaluation metrics. It converts the loss value to a floating point number, rounds it to 4 decimal places, and does the same for the accuracy. It then prints both values together on one line, giving a concise summary of the model's loss and accuracy on the dataset. This script shows how to handle variable length text sequences in a simple LSTM-based sentiment classifier using padding and masking. It prepares a small set of text phrases with sentiment labels, then converts the text into padded integer sequences so all inputs have the same length. A sequential model is built with an embedding layer that supports masking, followed by an LSTM layer and a final dense layer with a sigmoid activation for binary classification. The model is trained briefly on the toy dataset, then evaluated on the same data to report loss and accuracy. Overall, it demonstrates that padding combined with masking allows an LSTM model to learn effectively from sequences of different original lengths. Transformer encoder block. Multi-head attention basics. To understand multi-head attention, first focus on the basic idea of attention in sequence modeling. Attention lets each position in a sequence selectively focus on other positions, deciding which tokens are most relevant, instead of compressing all past information into a single state as recurrent networks do. For example, in the sentence about a book being fascinating, the word that indicates the action should focus on the word book as the subject. By computing weighted combinations of token representations, attention makes it easier to capture long-range dependencies and improves how models understand relationships between distant words in a sequence. Multi-head attention extends basic attention by using several parallel attention heads, each focusing on different relationships within the same input sequence. One head might capture short-range patterns, while another tracks longer-range semantic links. Because each head offers a distinct view of how tokens relate to one another, their outputs can be combined into a richer overall representation. This lets the model follow multiple aspects of complex events at once, such as who did what and when, within a single encoder block. Multi-head attention is effective for sequence modeling because it processes all tokens in parallel and does not depend on their order, unlike recurrent networks. This makes it efficient on modern hardware and allows each attention head to connect any two positions in a single step, capturing long-range dependencies important for tasks like document classification and text analysis. In a transformer encoder, multi-head attention lets each token build a context-aware representation by drawing on information from the entire sequence, preparing it for later stages such as classification or tagging. Python code. Multi-head attention basics. This material introduces the basic ideas behind multi-head attention using a very small example built with TensorFlow. It walks you through how the mechanism works in a simple, step-by-step way. To follow along with the explanation, you are expected to run the code cells in order so you can see how each part of the model behaves. Overall, the goal is to give you an intuitive understanding of multi-head attention in a practical, hands-on manner. The script starts with a commented reminder to install TensorFlow version 2.20.0. Even though this line is not executed, it indicates the specific version required for the code to run correctly. Its purpose is to guide you in setting up a compatible environment before you actually run the script. Ensuring the correct TensorFlow version helps avoid errors and compatibility issues later on. We begin by importing TensorFlow, a key library used to build and train machine learning models. This import is necessary because the script relies on TensorFlow's tools to define and work with neural network layers. In particular, we will use these tools to construct and demonstrate how multi-head attention operates within a neural network. We use TensorFlow's random module to set a random seed so that any operations involving randomness give the same results every time the code runs. This makes our experiments reproducible, meaning we can reliably repeat them and get consistent outcomes. Reproducibility is important because it allows us to verify results and compare different runs in a fair and controlled way. This line of code prints the version of TensorFlow currently in use. It provides a quick check that the intended version of the library is installed and running. Confirming the version helps ensure that the rest of the code will be compatible with the TensorFlow features and behavior you expect. We create a small batch of token ID sequences using a TensorFlow constant, which gives us a two-dimensional tensor with two sequences. The first sequence is 1, 2, 3, followed by a 0, and the second is 4, 5, followed by two zeros. These zeros act as padding values so that both sequences have the same length. This padding makes it easier for neural networks to process the sequences in a consistent way. We print the shape of the toy token ID tensor to check its dimensions. This quick check confirms that the input data is structured as expected. Verifying the shape helps us catch mistakes early. Once the dimensions look correct, we can safely move on to later processing steps. We begin by setting a few key hyperparameters for our model. The vocabulary size is set to 20, which is the number of different tokens the model can represent. Each token is mapped to an 8-dimensional embedding vector, defining the size of the token representations. We also use 2 attention heads so the model can focus on different parts of the input sequence at the same time. Together, these choices configure how the embedding and attention components of the model operate. We use an embedding layer from TensorFlow's Keras library to turn token identifiers into dense numerical vectors. The size of the vocabulary and the length of each vector are controlled by 2 parameters. This layer maps each token ID to its vector representation, which is then used as input to neural network models. In this way, the models can process and learn from the original tokenized data more effectively. The code takes each toy token identifier and sends it through an embedding layer, which turns it into a dense vector. This converts the original discrete token identifiers into continuous numerical representations. Such continuous vectors are better suited for neural network processing. This embedding step is essential because it allows the model to capture semantic relationships between tokens in the sequence. We check the shape of the embedded tokens tensor to confirm it matches what we expect. This verification step ensures that the embedding layer has correctly converted the input token identifiers into dense vectors. Having the right dimensions is essential so that all later layers in the model can process these embeddings properly. To build a padding mask, we first check which token IDs are not 0, which tells us where the sequence has real tokens instead of padding. We then turn this result into a floating point tensor. This mask is later used by the attention mechanism, so it can focus only on the non-padded positions and ignore the padding during processing. We reshape the padding mask used for attention so it matches the input format expected by the multi-head attention layer. The original mask marks which positions in each token sequence contain real tokens rather than padding. By inserting 2 extra dimensions into this mask, we convert it into the required 4-dimensional shape. This allows the attention mechanism to correctly apply the mask and ignore padded positions during its computations. We print the shape of the attention mask to confirm that its dimensions are correct. This check makes sure the mask matches what the attention mechanism expects as input. When the shape is correct, the model can properly ignore padded positions during attention calculations. Verifying this prevents shape mismatches that could lead to incorrect behavior in the attention step. We build a multi-head attention layer using TensorFlow's Keras library, configured for self-attention so that the same input provides the queries, keys, and values. The number of attention heads and the size of the embeddings are controlled by two parameters. By splitting attention into multiple heads, the model can focus on different parts of the input sequence at the same time. This helps it capture more complex patterns and relationships within the data. We assign the embedded tokens to what we call the query tensor, and this step is important because self-attention uses the same underlying data for queries, keys, and values. By feeding the embedded tokens into all three roles, the model can compare each token to every other token in the sequence. This allows it to focus attention on different parts of the input when computing these comparisons. As a result, the model can effectively capture relationships within the sequence. We now apply multi-head self-attention using the layer defined earlier, where the query, key, and value are all the same embedded token representations. This setup is standard for self-attention because it lets each token attend to every other token in the sequence. We also pass in an attention mask so that padded positions are ignored during the attention computation. Finally, we ask the layer to return both the attended outputs and the attention scores, so we can examine how attention is distributed across the tokens. We print the shape of the attended output tensor to verify that the multi-head attention layer is producing data with the expected dimensions. This check confirms that the output size is correct and compatible with the next stages of the model. By validating the tensor shape at this point, we ensure the attention layer is working as intended for further processing. We print the shape of the attention scores tensor to confirm its dimensions. This check verifies that the attention mechanism is producing outputs with the expected size. Ensuring the tensor shape matches our design is crucial for the model's computations to be correct. By validating these dimensions, we help confirm that the attention component is working as intended within the overall model. We compute the average attention scores by taking the mean across all attention heads. Using a reduce mean operation along the head dimension, we combine the separate head scores into one set of values. This produces a single, unified attention map that is easier to interpret than multiple separate heads, while still reflecting their overall behavior. To make the attention scores easier to read, we rescale and round them. We first multiply the mean scores by 10, so the values are larger and more noticeable. Then we round these scaled values to the nearest whole number. Finally, we divide by 10 to return them to the original scale, now rounded to 1 decimal place. This simple procedure makes the scores more compact and readable. The code announces that it will show a sample of the mean attention scores, then displays the process scores for the first sequence. These scores have been averaged across all attention heads and rounded to make them easier to read. This step helps you see how attention is distributed over the tokens in the sequence in a more interpretable form. We now display the attention scores for the first input sequence after averaging them across all attention heads and rounding the values. This simplification makes the scores easier to read and interpret. By examining these scores, we can see how the model distributes its focus across different parts of the input. In other words, it shows which tokens in the sequence the model considers most important when making its predictions. This script gives a simple demonstration of multi-head attention in TensorFlow. It begins by fixing the random seed, then creates a small batch of token sequences and converts them into dense vector embeddings. A padding mask is built so that padded positions are ignored, and a multi-head attention layer is applied in a self-attention setup where queries, keys, and values are the same. The script prints the shapes of the attention outputs and scores to confirm they match expectations, then averages the attention scores across heads, rounds them, and shows a sample for the first sequence. This final step illustrates how attention is distributed across tokens in the input. Residual connections and normalization. Residual connections and normalization are key to making transformer encoder blocks train effectively and stay stable. A residual or skip connection lets the original input bypass a sublayer and be added back to its output, acting as a safety net for information and gradients. This helps gradients flow through many layers, reduces vanishing gradient problems, and supports deeper models. In a Keras-based encoder, you route the input around the attention or feed-forward sublayer, and then combine it with the sublayer output, so the final tensor contains both the transformed features and the original signal. Layer normalization works together with residual connections to stabilize training, especially for variable length sequences in natural language processing. After adding the residual connection, layer normalization rescales the features for each example so the activations stay in a range that is easier for the optimizer to handle. This reduces sensitivity to weight initialization and learning rate and helps maintain numerical stability token by token across a sequence. In Keras, this is typically done by placing a normalization layer immediately after the residual addition. In a transformer encoder block, residual connections combined with normalization create a stable pattern that supports deep sequence modeling. Each block applies this pattern to both the multi-head attention and the feed-forward layer by adding the input back to the output and then normalizing. This setup lets the model gradually refine its internal representations, which is important for tasks like sentiment analysis and intent detection. It also keeps Keras implementations modular and scalable, allowing many encoder blocks to be stacked while reducing training difficulties and sensitivity to hyperparameters. Python code, residual connections and normalization. This script demonstrates how to build a very small transformer encoder using Keras, focusing on residual connections and normalization. It constructs the core encoder structure, then applies it to a simple text classification task. The model is trained briefly on dummy data, serving mainly as a compact example of how these transformer components work together in practice. The commented line recommends installing TensorFlow version 2.20.0, which is a specific release of this machine learning library. Using this exact version helps ensure that the code that follows will run correctly. It avoids potential problems that might occur if newer versions introduce changes that are not compatible with the existing code. This code begins by importing 3 key Python libraries. It imports the operating system library to work with files and environment settings, the random library to generate random numbers for tasks like shuffling or sampling, and the numerical computing library NumPy to efficiently handle arrays and perform mathematical operations. Together, these imports prepare the program to manage system resources, use randomness, and carry out fast numerical calculations. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers module from Keras, which provides components like dense and convolutional layers. Together, these imports give us the essential tools to define and train our neural network model. To make our results repeatable each time the program runs, we fix the random seed to a specific value, such as 42. We first set this seed for Python's built-in random number generator, then for NumPy's random number generator, and finally for TensorFlow's random number generator. Doing this ensures that all random operations across these libraries behave deterministically. This reproducible setup is especially important when training and evaluating machine learning models. This line displays the version of TensorFlow that is currently in use. It provides a quick check that the correct version of the library is installed. Confirming the version helps ensure compatibility and that the code will run as expected. We define a small dataset for a text classification task by setting a few key parameters. There are 64 samples, meaning 64 separate data points. Each sample is a sequence of 10 integers, and these integers are drawn from a vocabulary of 50 possible values. The problem has two classes, so it is a binary classification task. This code creates random integer sequences to mimic tokenized text data. It uses a numerical library's random integer generator to build an array where each number stands for a token. The array size is set by how many samples you want and how long each sequence should be. In effect, it simulates a batch of fixed-length text sequences with tokens drawn from a vocabulary of a chosen size. This code creates random binary labels for a classification task. It uses a random integer function from a numerical library to generate zeros and ones, which represent the two classes. The number of generated labels matches the number of samples, so each sample receives exactly one corresponding class label. We set the training set size to 48, meaning we use the first 48 samples from our dataset for training and the rest for validation. We split both the input data and the labels at this point, so each has a training part and a validation part. This setup lets us train the model on one portion of the data and then check its performance on separate data. Doing so helps us see how well the model is likely to generalize to new, unseen examples. We define a simple transformer encoder class that extends a Keras layer and initializes the key parts of a transformer block. It includes a multi-head attention layer with a chosen number of heads and embedding dimension, so the model can attend to different parts of the input sequence at once. It also builds a small feed-forward network with two dense layers, where the first uses a ReLU activation to expand the representation, and the second projects it back to the original embedding size. Finally, two-layer normalization components are added to stabilize training and help maintain the model's performance. In this process, the model first applies multi-head attention to the input so it can focus on different parts of the sequence at once, then adds this attention output back to the original input to form a residual connection. Layer normalization is applied to this sum to stabilize learning, and the result is passed through a feed-forward neural network that further transforms the data. The output of this feed-forward network is again added back to the normalized data, creating a second residual connection. Finally, another layer normalization is applied, producing an output that is well prepared for the next layers and helping the model learn complex patterns effectively. We define key hyperparameters that shape the transformer model. The embedding dimension is set to 16, which controls the size of the vector space used to represent tokens. The number of attention heads is set to 2, determining how many separate attention mechanisms run in parallel. The feed-forward dimension is set to 32, which specifies the size of the internal feed-forward network in each encoder block. Together, these values configure the model's architecture and strongly influence its performance. We begin by creating the input layer for our Keras model, which receives sequences that all have the same fixed length. These inputs are stored as integers, which is standard for tokenized text, where each word or token is mapped to an integer index. This input layer is the model's entry point, where the raw integer sequences are provided so they can be processed by the following layers. We begin by converting the input tokens, which are integers, into dense vectors using an embedding layer from Keras. This layer maps each token index from the vocabulary into a continuous vector space with a chosen embedding dimension. By doing this, the model replaces discrete token IDs with richer numerical representations that can capture semantic relationships between tokens. The output is a sequence where each original token is now represented by a dense vector, ready for further processing in the model. We apply a custom transformer encoder block to the embedded input by first creating an instance of the encoder with a chosen embedding size, number of attention heads, and feed-forward dimension. This configuration sets up the internal layers needed to process the data. We then pass the embedded input through this encoder, which uses multi-head attention, residual connections, and layer normalization to refine the representation. The result is a more informative version of the input that is ready for the next stages of the model. The model applies global average pooling to turn the whole sequence of encoded representations into one fixed-size vector. It does this by averaging each feature across all positions in the sequence, creating a compact summary of the input. This step reduces the dimensionality of the data and produces a single pooled vector. That vector is then passed to the final dense layer, which performs the classification. We finish the model by adding a dense layer that acts as the final classification layer. It has one unit for each class we want to predict, which in this example is 2. This layer uses the softmax activation function, which turns the raw outputs into a probability distribution over the classes. As a result, for each input sequence, the model produces predicted probabilities for each possible class. To build the final model in Keras, we first define a model object that connects the inputs to the outputs we prepared earlier. We then compile the model, which configures it for training. In this step, we choose the Atom optimizer for efficient and adaptive learning, and use sparse categorical cross-entropy as the loss function, since we are doing classification with integer labels. We also track accuracy as a metric, so we can monitor how well the model performs during training and validation. Before training, we first check that the model's output shape is correct by running a small batch of data through it. Typically, we take the first 2 samples from the training set and pass them through the model. We then print or inspect the shape of the resulting output to see if it matches what we expect. This quick verification step helps confirm that the model's architecture is set up properly before we invest time in full training or evaluation. The model is trained using a fit procedure that takes training data and labels, along with separate validation data to track performance. Training runs for 3 epochs, so the model goes through the entire dataset 3 times. A batch size of 8 is used, meaning the model updates its weights after every 8 samples. The verbose setting is turned off, so the training process runs without displaying any output. This step evaluates how well the trained model performs on the validation data. It uses Keras's evaluation function to compute the model's loss and accuracy on the validation features and labels. The evaluation runs silently, without printing progress, and returns these performance metrics. By checking these results, you can see how well the model is likely to generalize to new, unseen data. The code first prints the validation loss as a floating point number, giving a measure of how well the model performs on unseen data. It then prints the validation accuracy, also as a floating point number, showing the percentage of correct predictions on the validation set. Finally, it reports that the encoder block uses residual connections and layer normalization, highlighting key architectural features that support the model's performance. This material describes a simple transformer encoder built with Keras to highlight how residual connections and layer normalization improve training. A small dummy dataset of integer sequences is used for a binary classification task. The model includes an embedding layer, a custom transformer encoder block with multi-head attention, and a feed-forward network, with residual connections and normalization applied around these components. It is trained briefly with the Atom optimizer and then evaluated on a validation set, reporting loss and accuracy. The main point is to show that adding residual connections and layer normalization helps stabilize and enhance the encoder's performance. Feed-forward layers explained. In a transformer encoder block, the feed-forward layer refines the token representations produced by multi-head attention into more abstract features. It is a small neural network applied separately and identically to each token. For each token, its vector is first expanded to a higher dimension, passed through a nonlinear activation, and then reduced back to its original size. This lets the model learn complex feature combinations for each token, while keeping the sequence length and token alignment unchanged. In a transformer, the feed-forward sublayer applies the same small network to every position in a sequence, which keeps the model efficient while still expressive. It temporarily expands the dimensionality of each token's representation so it can capture complex patterns such as entities or sentiment. A nonlinear activation function, often a rectified linear unit, lets the network model complex decision boundaries. After attention has mixed information across tokens, this feed-forward step refines each token's representation for tasks like classification or tagging. In a transformer encoder block implemented with Keras, the feed-forward component acts independently on each time step, so it can be built using standard dense layers applied to the last dimension of the sequence tensor. After the attention mechanism provides contextualized representations, this feed-forward network refines them by emphasizing features that matter for the task and suppressing noise. Together with residual connections and normalization, it forms a strong building block that can be stacked multiple times. Adjusting the size of the intermediate layer, the choice of activation function, and the amount of dropout influences how well the model generalizes to new data. Python code, feed-forward layers explained. This material introduces transformer feed-forward layers in a simple way. It walks through building a very small encoder block using Keras components, focusing on how the feed-forward part fits into the overall structure. To make the ideas concrete, it briefly trains this tiny model on toy text data, so you can see how the pieces work together in practice. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It forces the environment to use this exact version, so the code behaves as expected. This is important for compatibility and for being able to reproduce results. The exclamation mark shows that the command is intended to be run in a Jupyter notebook or a similar tool that can execute shell commands directly. We begin by importing 3 key Python libraries to prepare our script. The operating system library lets us interact with the system, for example by working with files or environment settings. The random library provides tools for generating random numbers and performing random operations. The numerical computing library NumPy gives us efficient support for arrays and mathematical calculations. Together, these imports set up the basic tools we need for data manipulation and processing in the rest of the program. To make our code produce the same results every time it runs, we set deterministic seeds for randomness. We first set a seed with the value 7 using the random library so that any random operations are repeatable. We then set another seed, also with the value 7, for the random number generator in the numerical library. Using these seeds ensures that all random numbers generated in the script are consistent and reproducible across different runs. We start by importing TensorFlow, a library used to build and train machine learning models. From TensorFlow, we also use the Keras module, which offers a simpler, high-level way to define neural network layers and models. This combination lets us rely on TensorFlow's powerful features while using Keras to make model building more intuitive and efficient. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check that TensorFlow is installed correctly and matches what the rest of the program expects. Knowing the exact version matters because different versions can change features or syntax, which may affect how the code runs. This code uses TensorFlow to check whether any physical graphics processing units are available. If at least one GPU is found, it sets the device so that computations run on the GPU, which can speed up execution. If no GPU is available, it automatically falls back to using the central processing unit instead. This setup helps the program make efficient use of whatever hardware is present. The code checks whether a physical GPU is available, and then prints which device will be used for computations. If a GPU is found, it selects the GPU. Otherwise, it falls back to the CPU. This message helps you understand the hardware context in which the model will run, which can affect performance. We begin with a small set of simple example sentences that serve as input data for our model. Each sentence is a short movie review or opinion expressed as a text string. Using these examples, we set up a basic text classification task. The goal is for the model to learn to distinguish between positive and negative sentiments based on the patterns it finds in these sentences. We assign binary sentiment labels to our sentences using a numerical array, where 1 represents positive sentiment and 0 represents negative sentiment. This creates a simple machine-readable way to distinguish between the two classes. We store these labels using a 32-bit integer type to keep memory use efficient and support fast computation. We use a tokenizer from Keras to turn text into sequences of integers that a model can process. It is configured to keep only the 50 most frequent words in the dataset. This limits the vocabulary size and helps the model focus on the most important and commonly used words for the task. The tokenizer is being trained on a small text dataset to prepare it for use in a model. It analyzes the text to build a vocabulary of all the words it finds. Each word is then assigned a unique integer index, usually based on how often it appears. These indices are later used to convert the original text into sequences of numbers. This numerical representation is essential for the model to process and learn from the text data. This process takes a list of text sentences and converts each one into a sequence of integers using a Keras tokenizer that was previously trained on the text. Each word is replaced by a unique number based on the tokenizer's learned vocabulary. This step is crucial because neural networks work with numerical data, not raw text. By turning words into integer sequences, the text becomes suitable input for training and running the model. We set a maximum sequence length of 6 so that all inputs to the neural network have the same size, which is necessary for efficient batch processing. To achieve this, we use Keras preprocessing to pad shorter sequences by adding zeros until they reach this fixed length. The zeros are added after the original sequence, so the order of the existing tokens is preserved, while still producing uniform input lengths. The padded sequences are converted into a tensor of integers so they can be used as input to the neural network. This conversion uses a numerical library to put the data into the proper format. By setting the data type to 32-bit integers, the code matches the model's expected input type. This is important because tokenized text data is typically represented as integer values that the model can process correctly. The code prints the shape of the input array that holds the padded, tokenized text sequences. This check confirms that the data has the correct dimensions before you build and train the model. By verifying the shape, you make sure the input format matches what the model expects. This helps prevent dimension mismatches and related errors during training. We define several key hyperparameters for our encoder model. The vocabulary size is set to 50, which limits how many unique words the tokenizer can represent. The model dimension is 16, meaning each token is mapped to a dense vector of length 16. The feed-forward dimension is 32, giving the intermediate layer in the feed-forward network more capacity for complex transformations. Finally, we use 2 attention heads so the model can focus on different parts of the input sequence at the same time and better capture different aspects of the data. We begin by defining an input layer in Keras that receives sequences of token IDs, which are integer representations of words in our text data. The length of these sequences is fixed by the maximum sequence length we chose earlier, so each input example has the same shape. This input layer is the entry point of our neural network, allowing the model to treat each sequence of token IDs as a single input unit. By setting the data type to 32-bit integers, we ensure efficient handling of these non-negative token ID values. In Keras, we use an embedding layer to turn input tokens into dense numerical vectors. The input dimension is set to the vocabulary size, which is the number of different tokens the model can handle. The output dimension is the model's embedding size, which controls how large each vector is. This step is essential because it converts discrete token IDs into continuous vector representations that neural networks can process effectively. The embedding layer takes the input token IDs and converts each one into a dense vector. These vectors represent the semantic meaning of the tokens in a continuous space instead of using raw discrete IDs. By mapping each token to a vector of a chosen dimension, the model can process and compare words more effectively. This step is essential for learning relationships between words based on how they appear together in the training data. We generate a sequence of numbers starting at 0 and going up to, but not including, the maximum length of the input sequences. These numbers act as position indices for the tokens in each sequence. Using TensorFlow's range function, we create these indices so we can later add positional information to the token embeddings. This helps the model understand and use the order of words in a sentence. We use a positional embedding layer to assign each position in the input sequence a dense vector with the same size as the token embeddings. By doing this, positional information is encoded in the same space as the token representations. This allows the model to understand the order of tokens and distinguish between them based on where they appear in the sequence. The model uses a positional embedding layer to assign a position representation to each place in the input sequence, and this is applied across the entire batch of sequences. By adding these positional embeddings, every token becomes aware of where it appears in the sequence. This information is essential for the transformer to preserve and use the order of tokens when processing the data. This step in the model combines 2 types of embeddings: token embeddings, which capture the meaning of each word, and positional embeddings, which capture where each word appears in the sequence. By adding these together, the model encodes both what each word means and its position in the sentence. This combined representation is stored as encoded tokens and is then passed on to the later layers of the model for further processing and understanding of context and word order. We use a multi-head self-attention layer in Keras, so the model can focus on different parts of an input sequence at the same time. By choosing the number of attention heads and the size of the key vectors, we control how the attention mechanism processes the data. This configuration is important because it helps the model capture complex relationships within the sequence and learn more effectively from the input. The model applies a multi-head self-attention layer to the encoded tokens, using the same tensor as the queries, keys, and values. This lets the model compare each token to every other token in the sequence and compute attention scores. Through this process, it can focus on the most relevant parts of the input when representing each token. The result is an attention output that provides contextually enriched token representations within the same sequence. In this step, we add a residual connection around the attention output by summing the original encoded tokens with the attention layer's output. This keeps the original input information while blending in the attention-enhanced features. Using this residual connection helps stabilize training and ensures important details from the input are not lost during the transformation. The code uses layer normalization on the attention output to stabilize training. It does this by normalizing the feature values for each input, so they have a mean of 0 and a variance of 1. A small constant called epsilon is added during this process to avoid division by 0 and keep the computation numerically stable. This part of the network defines the first dense layer in the feed-forward block, whose main role is to expand the dimensionality of the input. It uses the rectified linear unit activation function to introduce nonlinearity, which helps the model learn more complex patterns. The output size of this layer is set to the larger feed-forward dimension, allowing the network to represent and capture more features than are present in the original input. The second dense layer reduces the representation back to the model's original dimension by using an output size equal to the model dimension. This step keeps the architecture consistent so that the output fits what the following layers expect. It allows the network to perform complex transformations in between while still returning to the standard model size at the end of the block. In this step, the model applies the first dense layer to the normalized attention output as part of the transformer's feed-forward network. This dense layer takes the normalized attention results and increases their dimensionality. By expanding the representation, it helps the model capture more complex patterns and relationships in the data. This improves the transformer's ability to learn from the input and generalize to new examples. In this model, dropout is applied to the intermediate feed-forward layer as a way to reduce overfitting. Dropout works by randomly setting a portion of the layer's units to 0 during training, so the model cannot rely too much on any single neuron. Here, 10% of the units in that intermediate layer are dropped. This encourages the network to learn more robust patterns and improves its ability to generalize to new data. Next, the second dense layer is applied to the intermediate feed-forward output, reducing it back to the original model dimension. This step reverses the earlier expansion and returns the data to the same size as the initial embeddings. Doing so keeps the model's architecture consistent and ensures that later layers can process the data correctly. In short, this layer completes the feed-forward block by transforming the expanded representation back to the model's standard size. Here we add a residual connection around the feed-forward network by summing the output of the layer-normalized attention with the output of the feed-forward layer. This shortcut path helps gradients flow more easily during training. As a result, the model can learn more effectively because gradients can bypass the feed-forward layer when needed. This type of residual connection is a standard technique in deep learning to improve performance and stability. The code applies layer normalization to the feed-forward residual output to help stabilize training. By normalizing the output across features, it keeps the mean and variance of the activations under control. This stabilization can speed up convergence and improve the overall performance of the model. The model uses a global average pooling layer from Keras to process the output of the feed-forward network. This layer takes all the token representations in the sequence and averages them over the sequence length. The result is a single pooled vector that summarizes the entire input sequence. This compact representation is then used as the input for later classification steps. We add a dense layer with a single output unit, which is standard for binary classification. This layer uses a sigmoid activation function, so its output is a value between 0 and 1 that can be interpreted as a probability. We feed into this layer the pooled output from the previous step, which is the averaged representation of all tokens in the input. With this setup, the model predicts how likely it is that the input belongs to one of the two classes. We build a Keras model by defining its inputs as the tokenized sequences and its outputs as the logits produced by the final dense layer. This connects the input data through all intermediate layers to the final predictions, establishing the model's architecture. Once this structure is defined, we can use Keras's high-level tools to compile and train the model efficiently. The model is now being compiled, which prepares it for training. It uses the Atom optimizer, which efficiently adjusts learning rates during learning. The loss function is binary cross-entropy, which is appropriate for binary classification because it measures how far the predictions are from the true labels. During training and evaluation, the model will also track accuracy to show how often its predictions match the correct answers. The model is trained using the Keras fit method, which takes the tokenized and padded text sequences as input and their sentiment labels as targets. Training runs for 10 epochs, so the model goes through the entire dataset 10 times to refine its weights. A batch size of 2 means it updates its weights after processing 2 samples at a time. The verbose setting is turned off to suppress training progress messages and keep the console output uncluttered. The code checks how well the model performs on the same small dataset it was trained on by calling the model's evaluation function with the input data and their labels. This function calculates the loss and accuracy for that data. The evaluation runs silently without showing progress. The resulting loss and accuracy values are then stored for later use or inspection. This code reports how well the model has learned by printing its training accuracy on a small dataset. It displays a short message that summarizes the model's performance. The accuracy value is rounded to 3 decimal places, so the result is clear, concise, and easy to interpret. We begin by selecting the first example from the input data, so we have a single, clear sequence to work with. By slicing the input to keep only this first element, we isolate one piece of tokenized and padded text. This focused example lets us closely examine how the model processes the data and how its representation changes as it moves through the feed-forward layers. We build an intermediate version of our neural network to inspect specific internal tensor outputs. It uses the same input layer as the main model, which takes sequences of token IDs, but instead of producing the final classification, it outputs 2 internal results. These are the normalized attention output and the normalized feed-forward output. By examining these tensors, we can see how the model transforms data at these stages and better understand its internal processing. The code uses an intermediate version of the model that has been configured to output the results of its attention and feed-forward layers. It runs a prediction on a small example taken from the input data, with verbose output turned off, so nothing extra is printed. By capturing these intermediate outputs, we can examine how the data is represented inside the model at different stages. This helps us understand how the model processes and transforms the input as it moves through its internal layers. The code first prints the shape of the attention output tensor to show how the multi-head attention mechanism processes the input sequence. It then prints the shape of the feed-forward output tensor to reveal how the feed-forward network further transforms that sequence. By comparing these shapes, we see that the model operates in a position-wise manner, meaning each token in the sequence is processed independently as it passes through the attention and feed-forward layers. This script builds a simple transformer encoder block in Keras to show how the feed-forward layers work on toy kex data. It prepares a few short sentences by tokenizing and padding them, then passes them through an embedding layer with positional information and a multi-head self-attention mechanism, each stabilized with residual connections and layer normalization. A two-layer feed-forward network with dropout is applied in the same way, again using residual connections and normalization. The model is compiled with an atom optimizer and binary cross-entropy loss, trained briefly on the small dataset, and then evaluated to report its accuracy. An additional intermediate model is used to inspect the shapes of the intention and feed-forward outputs, emphasizing that these layers operate in a position-wise manner across the sequence. Comparing sequence architectures, training stability, and speed. When comparing sequence models like LSTMs, GRUs, and transformers, focus on both training stability and speed. Stability means the loss decreases smoothly without erratic jumps and is not overly sensitive to choices like learning rate or batch size. Speed refers to how fast the model processes sequences and finishes epochs, which affects how many experiments you can run. In practical NLP work, a model that converges reliably, even if slightly less accurate, is often more useful than a theoretically stronger but unstable model. Understanding this trade-off helps you design experiments that are both rigorous and feasible. Recurrent models like LSTMs and GRUs process sequences step by step, which limits parallelism and can make training slow on long documents. Their gating mechanisms help control gradient flow and usually give smooth, stable training when hyperparameters are well-tuned, but poor settings can still cause vanishing or exploding gradients. In practice, an LSTM classifier may show steadily decreasing loss, yet require long epochs, while GRUs, being simpler, tend to train faster and more easily. However, both architectures still demand careful control of gradients and learning rates to achieve reliable convergence. Transformer encoders use self-attention to process entire sequences in parallel, which can greatly speed up training on modern hardware, especially for medium-length text. This parallelism comes with stability challenges, since transformers are sensitive to initialization and learning rate schedules, and often need techniques like warm-up to keep early training from becoming unstable. In real NLP tasks, such as classifying support tickets, they can reach high accuracy faster than LSTMs, but only when they are carefully tuned to avoid erratic behavior. Therefore, evaluating these models must consider not just training speed, but also how reliably they converge under realistic tuning efforts, which is essential for delivering dependable models quickly. Python code, training stability and speed. This script is designed to compare how stable and how fast different models train. It works with very small models and simple text data, so the focus stays on the training behavior. In particular, it examines and contrasts LSTM-based encoders with transformer-style encoders. The goal is to see how these two types of encoders differ in training speed and stability under similar conditions. The commented line recommends installing TensorFlow version 2.20.0 to keep your setup consistent and reliable. Locking in a specific version helps ensure that your code runs the same way across different machines and over time. This is important for reproducibility and stability when you run machine learning experiments, It also helps you avoid unexpected problems that can come from changes in newer versions of the library. We begin by importing several key modules needed for our work. The operating system module lets us interact with the system environment, and the time module provides tools for working with timing. We also import the random module to generate random numbers for tasks like setting seeds and shuffling data. Next, we bring in NumPy for efficient numerical computations with arrays. Finally, we import TensorFlow, which we will use to build and train machine learning models so we can compare their training stability and speed. We begin by setting a seed value of 42 so that all random number generation is consistent each time the code runs. We apply this seed to the random library, to NumPy, and to TensorFlow so that all their random operations are aligned. This makes the behavior of the program deterministic, which is important for debugging and for reliably comparing results across different runs. We begin by printing the TensorFlow version used in the script to understand the exact environment in which the code is running. This helps confirm compatibility with other tools and libraries. It is also important for debugging and reproducing results, since different TensorFlow versions can change features or behavior. Knowing the version makes it easier to track down issues and ensure that others can reliably repeat the same experiments. We begin with a small synthetic text dataset made of short sentences that act as simple movie reviews. Each sentence is designed to clearly express either a positive or negative sentiment. For instance, a sentence praising the movie and its acting represents a positive review, while one criticizing them represents a negative review. This controlled setup gives us an easy way to test and compare how different models perform on basic sentiment analysis tasks. This code assigns simple binary sentiment labels to each piece of text data, using 1 to indicate positive sentiment and 0 to indicate negative sentiment. These labels form the target outputs for a machine learning model. The model is then trained to learn patterns in the text that correspond to positive or negative sentiment. Once trained, it can predict the sentiment of new unseen text based on these learned patterns. The code turns the list of sentiment labels into a numeric array using integers. This step makes numerical processing more efficient and ensures the data is in a format that works well with TensorFlow. Because TensorFlow expects input data as arrays during model training, this conversion is necessary for the model to run properly. We define a small text vectorization layer to prepare text data for a model. The vocabulary is limited to 100 tokens, and each input text is converted into a sequence with a fixed length of 8. Any text longer than this is truncated, and shorter texts are padded so all sequences have the same length. Using the text vectorization layer from TensorFlow's Keras library, the processed output is a sequence of integers that represents the original text in this fixed format. The vectorizer is first adapted to the small set of text data, so it can learn the vocabulary and structure of the inputs. During this step, the text vectorization layer builds a mapping from words to integer indices based on how often and in what order words appear in the dataset. This learned mapping is essential because it converts raw text into numerical form. Once in this format, the data can be used effectively by machine learning models. The text data is first turned into a TensorFlow constant so it can be handled properly inside the TensorFlow framework. Then, a previously trained vectorizer is applied to this constant to convert the text into sequences of integers. Each integer corresponds to a token in the vocabulary. This numerical form of the text is what machine learning models need, since they can only work with numbers, not raw text. Before creating the datasets, the code verifies that the number of integer sequences matches the number of labels. This check confirms that every text input has a corresponding sentiment label. By doing this, It preserves data integrity and ensures the training process is based on correctly paired inputs and labels. We begin by choosing a batch size of 4, which controls how many samples are processed together. Then we build a TensorFlow dataset from the integer sequences and their labels. This dataset is shuffled with a buffer of 8 and a fixed random seed, so the data is well mixed and the process is reproducible. Finally, we group the data into batches using the chosen batch size so the model can train on manageable chunks at a time. To build this LSTM model, we define an input layer that matches the sequence length, then pass it through an embedding layer that maps tokens to dense vectors of size 16. This is followed by an LSTM layer with 16 units that processes the sequence. The output is a dense layer with 1 unit and a sigmoid activation, which is appropriate for binary classification. We then create the model by connecting the input and output, and compile it with the Atom optimizer using a learning rate of 0.01, binary cross-entropy as the loss, and accuracy as the evaluation metric, producing a model ready for training. A simple transformer-style encoder block takes an input sequence and first applies multi-head attention with a chosen number of heads and key dimensions, allowing the model to focus on different parts of the sequence at once. The attention output goes through dropout to reduce overfitting, then is added back to the original input and normalized to keep training stable. Next, a feed-forward network with a ReLU activation and an output layer matching the input dimension processes this result, followed by another dropout layer. Finally, this feed-forward output is added to the normalized representation and normalized again, completing an encoder block that can capture complex patterns while maintaining stable training behavior. This script compares the training stability and speed of 2 TensorFlow models, an LSTM and a transformer encoder, on a small synthetic text sentiment dataset. It sets a fixed random seed for reproducibility, vectorizes the text into integer sequences, and builds one model with an LSTM layer and another with a transformer encoder block. Both models use the Atom optimizer and binary cross-entropy loss and are trained for 5 epochs. The script measures and prints training time, loss, and accuracy for each model, then reports which one trained faster. On this kind of small dataset, the transformer often trains faster because it can process data in parallel, though the exact result can vary with the setup and data. Overfitting across architectures. When comparing overfitting in sequence models, it helps to look at how they use model capacity. Recurrent networks like LSTMs and GRUs compress the sequence into a hidden state, which can act as a form of regularization, but they still overfit if you add too many units or layers, especially with limited data. Transformers use self-attention to directly connect all positions in the sequence and typically have many more parameters, so they are very powerful but more prone to memorizing training patterns without strong regularization. As a result, transformers often drive training loss down quickly, but their validation loss can start increasing earlier than that of smaller recurrence models, signaling stronger overfitting. Overfitting depends on both the task and the model. For short text tasks like sentiment analysis, simple recurrent models such as LSTMs or GRUs often generalize well with little regularization because they have limited capacity. In contrast, deep transformer models can overfit by latching onto rare or spurious patterns in the training data, especially when the dataset is small. On longer documents, recurrent models may fail to capture long-range dependencies, while transformers handle them better but can still memorize document templates. Monitoring how training and validation performance diverge helps reveal when and how each model type is overfitting. To compare overfitting across different architectures, look at how training and validation performance change as you vary model size, regularization, and training time. For example, you might train a small GRU, a larger LSTM, and a compact transformer on the same data with consistent early stopping and dropout. If a model, such as the transformer, reaches high training accuracy but shows little or no gain in validation accuracy, its extra capacity is not improving generalization. By gradually increasing layers or units and watching for growing gaps between training and validation metrics, you can identify when overfitting begins and better match model capacity to the complexity of your language data. This script compares overfitting in two neural network architectures, a GRU-based model and a transformer-based model, for text classification on the IMDb dataset. It prepares the data with a limited vocabulary and fixed input length, then builds one model with an embedding layer followed by a GRU layer, and another with an embedding layer followed by multi-head attention. Both models use the atom optimizer and binary cross-entropy loss and are trained on the same data with a validation split for 4 epochs. After training, the script reports the final training and validation accuracies for each model, so you can see that the simpler GRU model may overfit less than the higher capacity transformer model. Choosing architectures for tasks. When choosing a sequence model for a language task, base your decision on the type and length of the text and the output you need, not on which model you know best. For short texts like reviews or headlines, recurrent models such as LSTMs and GRUs or simple transformer encoders usually work well, and the choice often comes down to training speed and available compute. For long texts like legal documents, transformers are often better because they can link distant parts of the sequence, but they demand more computational power. In low resource settings, a carefully tuned recurrent model, possibly with truncation, may be more practical. Overall, match the architecture to the text length, structure, and your computational budget. When choosing a model architecture, focus on the kind of language patterns your task requires. For tasks based on local patterns, such as sentiment or intent detection, both recurrent models and transformer encoders work well, so you can decide based on training stability and hardware. For tasks that depend on long-range relationships, like tracking entities across multiple sentences, transformers are usually better because they directly connect all tokens to each other. However, for real-time tasks, such as live speech transcription, recurrent models can be preferable since they process inputs step by step, maintain state efficiently, and update predictions with predictable latency, which can matter more than full self-attention. When choosing a model, base your decision on practical constraints and evaluation results rather than theory alone. Compare options not only on accuracy, but also on latency, memory usage, and how easy they are to deploy and maintain. For example, a transformer might offer higher accuracy or better multilingual generalization, but demands special hardware, while a GRU could be simpler to run and still perform well enough. Use real-world data to weigh these trade-offs and decide whether an LSTM, GRU, transformer, or a hybrid approach best fits your needs. In this lecture, you learn to build LSTM or GRU-based sequence models for text classification using tf.keras. Implement a simple transformer-style encoder block using Keras layers for sequence modeling, and evaluate and compare the performance of different sequence architectures on an NLP task. In the next module, Module 8, we will go over distributed training. Thank you for your attention. See you all in the next lecture.